It's just a matter of, what the problem looks like when we see it. So let's get a little vocabulary straight first of all. I know when you see this symbol right here, you think times, but nobody ever says V times U.
So what is it called?
When we do vector multiplication, the symbol matters. In regular multiplication, it doesn't. If I said 2 times 3, I could use that symbol or that symbol and it wouldn't matter. With vectors, it does matter. So this one is called the dot product. This one is called the cross product. And we're not going to talk about that one today. We're going to talk exclusively about the dot product today. And when we read it, remember, we don't say V times U. That makes us sound kind of goofy. We say V dot U. V dot U. This one's V cross U. This one's V dot U. Now, how does it work? Very, very simple. I'm going to write it down. You tell me what I did. The dot product of these two vectors. I'm doing these two first. The dot product of these two vectors is 2 times 6 plus negative 3 times 1. So the dot product would be 9. It's just a number. The dot product is just a number. So what did I do? How are you going to explain this to somebody who's absent today? It's real simple. What do we do?
2 times x times x plus y.
That's it. Say it again, Dan.
X times x plus y plus y.
Y times y. Yeah. So x times x, y times y, add them together. It's that easy. All right? So if I were going to be here tomorrow, we might have a little quiz, but I'm going to be in the hospital, so you're off the hook. But let's say we had vector D had coordinates 3, 2, and E had coordinates 5, 1. What would be the dot product of D and E? What would D dot E be? What would the dot product of those two vectors be?
2.
Think what Dan said. What would it be? 17. You said 17, you're right. One more time, how did we do that? We took x times x, y times y, and added them together. Okay? Now, if you watched your e-learning video, which you were all supposed to have watched, then you know what this means. Someone impress me. Someone show me you did the right thing. And watch that video that I so painstakingly made for you. What does this mean? Thank you, Victoria.
I is horizontal and J is vertical.
Right, so this is just another way of saying 2, negative 3. It's just a fancy way of saying 2, negative 3. I is your horizontal unit vector, J is your vertical unit vector. This says take 2 steps that way, 3 steps down. That's the vector 2, negative 3. What's this one?
4.
The vector 4, 1. What's the dot product then of these two vectors? 5. 2 times 4, negative 3 times 1, add them up in the plate, thank you, it's 5.
So I is horizontal.
Yep, you watched the video. Now, what usually happens, and those of you in physics know this, because you've done dot products in physics. You may not have called them a dot product, but when I do this operation, you'll see you've done this if you calculated work. Anybody here, who's in physics in here? We have no physics, oh, we have one. Have you ever talked about work, the concept of work? Yes, that's actually a vector dot product. You'll see how it works right here. We have two vectors forming an angle. Now this is a very common situation. You have two forces, let's say, acting at a certain angle. Maybe it's an airplane and the wind. Okay, again, if you watch the video, we had some airplane wind problems. Now, if if I want to find the dot product of these two vectors, I have a problem. Because what do I not have? In this scenario, I've got vector P and vector Q. I know how long they are, and I know they form an angle of 58 degrees. But what do I not have?
You have the
What do I not have? The coordinates. I don't have the vector coordinates. So I'm going to need a different way of finding the dot product. Because this way depends on taking x times x and y times y. And if I don't have x and y, then that's going to be hard to do, right? So what's my new strategy? Very, very simple. The dot product will be 10 times 7 times the cosine of 58. Now tell me how I did that. I want to find the dot product of two vectors that form an angle. The dot product of those two vectors was 10 times 7 times the cosine of 58. Where did the 10 and the 7 come from? Those were the lengths, the magnitudes. So I take the magnitude of the first vector times the magnitude of the second vector times what? Not the angle, the cosine of the angle. The angle between, or the included angle, however you want to describe that. So that one's going to require a calculator to do the dot product. But again, you're just going to get a number. The dot product is always just a number. And it's 37.09 is your dot product. All right, so if we had a situation where two vectors, one was 16, one was 23, and they formed an angle of 37 degrees, could you find the dot product? I'll call this one M and this one N. Could you find the dot product of these two vectors? Okay, what would M dot N be? Very simply, it would be 16 times 23 times cosine 37. That's it. So you have two ways of finding the dot product. Right? Depending on the situation that you have been given. If you are given coordinates, how do you find the dot product? X times x, y times y, add them together. If you're given a physical situation where you've got two vectors forming an angle, then how do you find the dot product? Magnitude times magnitude times cosine. Now, believe it or not, that just opened up a hugely powerful thing for you. Suppose I said to you, find the angle between vector A, which has coordinates 3, -2, and vector B, which has coordinates 1, 7. Now wait a minute, let me kind of get a visual of this. Here's vector A, 3 over 3 down 2, and 1, 7. Here's vector B. Now, my job is to find that angle. And I want you to think about this for a second. You have options. You just took a quiz where you found angles, right? So law sines and law cosines would be an option if you wanted to build a triangle and mess around with it that way. Might work. Would work. Be a hassle, but it would work. Riley?
Could you find like the dot product and then plug that in like for MN and like
beautiful, beautiful, beautiful. She says, this is for, we have two ways of finding the dot product. We know that the dot product of these two vectors, I have the coordinates, so real easy, what's the dot product? Negative 11. But I also know that the dot product is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. Now, can I find the magnitude of the first vector? I don't know it right now, but I know the coordinates are 3, -2. Can I find the magnitude? Oh, we talked about that last week. How are we going to do that? How are we going to find the magnitude of that vector? Kayla, you were going to say it, I thought. We could do the distance formula. What else did we decide we could do? No, we're not going to. These are already vector coordinates. They're not points. They're vector coordinates. Oh, guys, this is over 3 down 2. Can't we just do a Pythagorean theorem? So that would be 3 squared plus 2 squared. So the magnitude of that vector is √13. What's the magnitude of this one? It's over 1 up 7. So its magnitude would be √50. I'm not going to simplify that. I don't need to. So wait a minute. We calculated the dot product, x times x, y times y, added them up and got negative 11. But we know another way of doing the dot product is right here. So can I say this? Can I say negative 11 is √13 times √50 times cosine? Is that all right? And that's not the answer, but that tells me that the cosine is negative 11 divided by the square root of what's 13 times 50? 650? Double check that arithmetic. I should be able to do that in my head, but you know what? Oh, yeah. Now remember, what was our goal? Find the angle. I don't know the angle, but I know it's cosine. So what can I do? Second cosine, inverse cosine, arc cosine, whatever vocabulary you want to use. Don't forget to take the square root of that 650. And what did you get for that angle? Yep, about 115.56 degrees. So it's Monday morning. Some of you are thinking, oh, what's so cool about that? What's so cool about that is you can now find the angle between any two vectors. I'm going to give you a couple more. Let's try another example. Let's say vector C has coordinates 3, -2. I think I'm using the same vectors over and over again. Let's say 4, -2. And D has coordinates 1, 2. All right, let's find the angle between them. All right, so let's recap. How do we do this? How do we find the angle between two vectors? We find the dot product, and we have the coordinates. As long as you have the coordinates, the dot product's easy. C dot D would be what? That's interesting. I wonder what that's going to do. Let's continue and see what happens. What's the next step? Find the magnitude of each vector. Because the dot product is magnitude times cosine. So magnitude of this one, think about it, over 4 down 2. Think Pythagorean theorem, over 4 down 2. 16 4 square root of 20. D over 2, or excuse me, over 1 up 2, that'd be root 5, times the cosine of the angle I'm looking for, magnitude times cosine. So 0 equals the square root of 100 times cosine theta.
Yes.
So cosine theta equals what? 0. You should probably know that, but go ahead and type it in on your calculator. What angle has a cosine of 90? Second cosine.
90 degrees.
What did I say? Cosine of 90? I meant a cosine of 0. It's 90 degrees. Yes, 90 degrees. So tell me about these two vectors. If the angle between them is 90 degrees, they're perpendicular. Oh shoot. Remember all that new vocabulary we got last week? Well, in vector land, we don't say perpendicular. In vector land, we say orthogonal. Oh, don't ask me. I don't know. We just do. Just like we don't say length, we say magnitude. We don't say sum, we say resultants. I don't know. We call it orthogonal. The vectors are orthogonal. It means the same thing as perpendicular. Now, to show you in my last couple minutes how all the pieces fit together, think about this vector. It goes over 4 and down 2. What's its slope? If it goes over 4 and down 2, its slope would be what?
1/2.
Negative 2 over 4, which is negative 1/2. This one goes over 1 up 2. So what's his slope? 2 over 1. Look at that, kids. Do we expect those to be perpendicular orthogonal? Do we expect that? Yes, because their slopes are negative reciprocals. Now, you're saying to me, okay, Mrs. Ford, that's awesome. I can look at these and tell you they're orthogonal, so why do I have to go all through all this? When you get to 3 dimensions, then you don't have slope anymore. Slope is rise over run. Slope is a 2-dimensional thing. When you throw a z in there, all bets are off. If you want to know vectors are orthogonal in 3 dimensions, you have one way of doing it. You do the dot product. And if they are orthogonal, what will happen to the dot product? It will be 0. If you have a homework problem tonight and it says, are these two vectors orthogonal? They're all 2-dimensional. So if you want to know if they're orthogonal, you can do the slope. That will always work. You can also quickly do the dot product. If it's 0, you know they're orthogonal. Okay? Alright, so now you've got some problems to do. I put them on Schoology. I updated everything. I also want to remind you, because I'm going to be going for some time now, that your papers are due when? The 23rd of March. So that is 3 weeks from Wednesday. Your papers are due. So if you haven't started your written resolution yet, before it's time to get busy. Okay? Have a good week, everyone. I'll see you sometime next week. You gotta be here before the end of before the period starts. Before the period starts. You guys want my calculator?
I couldn't get a single one right.
Oh, thank you, Sarah.
I calculated with the radians. And I just couldn't get out of the school. I was getting sick.
Bye, honey.
That's
Don't forget to give that note to the parents. Okay, thank you.
It's better than like a 0.
Okay.